Okay.
Hello everyone. Our next talk is Teoman Yalçınkaya. Teoman is an undergrad math student at Boğaziçi University. He is starting his third year, and together we worked on groups of finite Morley rank. And I enjoyed a lot working with him, and I hope that you will also enjoy with the talk. And Teoman, I'm passing it to you.
Thank you, Dicle, and thank you for encouraging me to study such a great subject. And thank you all for being here and making possible this great event. My slide is about groups and representation of finite Morley rank, and we will listen to the adventure of algebraicity conjecture. But first, we need to know some basic model theory in order to understand the motivation and Morley rank. And if we have a language and a set, this set is called a structure equipped with some relations. And each relation is offset of m to the ni for some I. Usually model theories include functions and constants too, but here we can see them all as relations. In this example, you see addition in real numbers, and we can see all constants as unary relations. And a formula is basically a sentence saying something about a specific structure. For example, this formula is in the language of rings, and if we look at in real numbers, it has basically y is greater than x. And definable subsets are the main objects of model theory. They are specific subsets defined by specific formulas. For example, if we have a group and an element of G, centralizer of G in group G is defined by this first order formula. And not all subgroups have to be definable. For example, in an infinite group, a slope 2 subgroup need not to be definable. And in Morley rank, let M be an omega saturated structure. We define Morley rank inductively. In order to we have positive rank, this definable subset mustn't be an empty set. And if we can find disjoint definable infinite family of subset via i's, all of them rank greater than alpha, then the rank of x must be greater than alpha plus 1. We can look at vector spaces. We can see it more easily. For example, in a subset of a vector space, all affine subsets of the structure have little dimension of the main structure. And this axiom is about limit ordinal, but we don't care them because we always work with finite ordinals in this talk. You can see a picture of inductive step of the definition. If Morley rank of a structure is a finite ordinal, we say that it has finite Morley rank. And in algebraic closed field, for example, all have Morley rank 1. And I defined definable subsets separately, but we can define them all in the same time. This definition is less model theoretic and more algebraic. It contains all relations and is closed under Boolean operations like intersection and union or complement. It's closed under finite Cartesian operators, and it's closed under quotients. Some model theorists call this property interpretable, but we abuse notation and call all of them definable universe. And if K is an algebraically closed field, its constructible class and definable class coincides. It follows from theorems of Chevalier and Tarski. Morley tried to axiomatize groups of finite Morley rank in algebraic way and offered three axioms. This first axiom is the same thing with the model theoretic definition of Morley rank. This is the inductive step. And this axiom says basically this rank function is definable. And this rank function must be additive too. Horowitz offered these three axioms, but they are not complete to axiomatize all groups of finite Morley rank. So Poisson added the last axiom, elimination of infinity. Pre-image of an element for pre-image of an element, there must be upper bound L. Pre-image of B has at most L elements or it's infinity. And then Poisson showed that these two definition of Morley rank is equal, and Morley rank is equal rank function everywhere. You can find the proof in a wonderful book of Poisson stable groups. And groups of finite Morley rank show similarity between algebraic groups. This means similarity. One of the main similarities is descending chain condition. But before that, I want to define degree of a structure. If we have rank n a structure, we cannot put inside infinitely many subset of rank n. Then rank of the main structure would be n plus 1 at least. So there must be a upper bound, there must be a limit. This integer is fixed for a structure and called degree. And if K is a subgroup of H, and then if ranks and groups is equal, they must be equal. This theorem is descending chain condition, and it says that every descending sequence of definable subgroups terminates. And proof uses rank and degree. And we need some definitions too. Connected component of a group is smallest definable subgroup of finite index, but there is no topology here. So if we have topology like in complex numbers, this is really the connected component. And the proof of it uses descending chain condition. And the group structure is connected, it has no proper definable subgroup of finite index. Further, it's important to us because it says three equivalent definition of being connected. E is connected if and only if it's equal to its connected part or its degree 1. And we defined rank function and groups of finite Morley rank. Now we are gonna look in small ranks 1, 2, and 3. Our main conjecture is a simple group, a simple infinite rank group is isomorphic to an algebraic group, so over some algebraically closed field as just a group, as an abstract group, because we don't care morphisms like thing in algebraic groups. And this is the image of this conjecture. We see all groups here. And groups of finite Morley rank is the extension of affine algebraic groups. We have other examples. And in simple group case, we don't know if is there anything here. We don't know if there is a simple group of finite Morley rank, which is not a affine algebraic group. And the conjecture says that there is nothing here. Rank 1 and 2 is almost trivial. A connected group of rank 1 is abelian, and it's isomorphic to either additive or multiplicative group of an algebraically closed field. And this is this situation is the same in algebraic groups too. And a theorem by Cherlin, a connected group of rank 2 is solvable. This is the same in algebraic group theory also. And before jump into rank 3, we need to make some definitions. Borel subgroup, maybe you are familiar with Borel subgroups from group theory or linear algebra. In matrix group, they exist as groups conjugate to upper triangular matrix group. But here we are a more abstract definition. Borel subgroup is maximal, definable, connected, and solvable subgroup. And in algebraic groups, they have some properties like they are self-normalizing. They are non-nilpotent as soon as G is non-nilpotent. They are centerless as soon as G is centerless. They cover G by conjugation, and they are all conjugate. And these properties hold in groups of finite Morley rank too. And an important definition for group theories is involution. Involution is the element of a group which has degree 2. And in our conjecture, there are 3 types of groups of finite Morley ranks. First part is degenerate. They do not contain any involution, and this will be important to us. We don't care other 2 cases. The important is if there is no involution in a group of finite Morley rank, then it's not a bad group. Bad group simply means a counterexample to our conjecture. It's a theorem by Franklin. And in rank 3, we know that there is no involution, thanks to Agnes'in. And so we know that there is no any bad group. So conjecture holds in rank 3 too. In order to prove this, we introduce a geometry on G. We have a lemma, all involutions are conjugate in this group, and every Borel subgroup B contains a unique involution I. So in order to get a contradiction, suppose there is an involution. So we will introduce a geometry. Points of this geometry is elements of G, and lines are something like B, E, D, B, H, and we can see them as like we have a Borel subgroup, and I replace G with G, H inverse B. It's better to understand. There are conjugates of Borel subgroup. We know that they are all conjugates and cover G. And we multiply with G from left. So I get it translates and cover all the plane. We can define lines in this fashion. And planes are G times I, where G is an involution. Our lemma is this triple G, lambda, and I is a projective 3 space. First axiom is, this is axioms of projective 3 spaces. Any 2 distinct points lie on a unique line. We can find such a line, namely Borel subgroup of this involution, X inverse Y, and translate them by X. And axiom 2 states that a line and a no-incidence point define a unique plane. We can prove it from previous 2 axioms. And you can see all 6 axioms hold in this structure. You can verify them. And we know that every projective 3 space is Argesian, which means it satisfies Desargues' theorem. And a theorem by Hilbert states that every projective space satisfying Desargues' theorem is coordinizable, which means we can find F skew field that G is isomorphic to projective 3 space over K. And model theory part say that K is definable field, and it's actually an algebraically closed commutative field. This is the theorem by Cherlin-Zilber and McIntyre. And we have action of G. G acts on itself by left from and multiply from left. And this action covers lines because we have lines like that. And if I multiply from left with any elements, it's still a line. And and it preserves incidence relations. So this action gives us an automorphism of this projective space. So G is simple. We can embed it in PGL for K. Then algebraic geometry finished the proof. Borel's fixed point theorem says that an action of an algebraic group fixes on a complete variety fixes at least one point. But action of G was left multiplication action, so we can't have a fixed point unless our element is trivial. So we have a contradiction. G has no involution. So this finished our proof that there is no bed group in rank 3 and algebraicity conjecture hold in rank 3. Now we are going to look at some representation of finite Morley ranks because borrowing tried to transfer methods of classification of finite simple groups into groups of finite Morley rank, and their representation theory is important in their classification problem. So we can apply these techniques in here. We work always in a definable universe, and G is a definable infinite group, acting on definably on a definable abelian group. Usually, when we say representation, we look at its linear action on vector spaces, but here we look at only abelian groups. Irreducible module is, we say a module irreducible if and only if there is no definable proper infinite G invariant subgroup of V. And definable endomorphisms of V denoted as step and V. All elements of this set is definable, but this set need not to be definable. Linearization theorem is an important theorem in order to see any group of finite Morley rank as a linear group. We define K as centralizer of G in definable endomorphism of V. Then K is algebraically closed field, and V is finite dimensional. We can embed G in GLV definably. The module of finite Morley rank is a triple, like G, V, and its action, where G is an infinite group and V is connected infinite group. Connectedness is important in this case. And all three is definable in a larger structure of group, larger structure of finite Morley rank. This structure can be a semi-direct product of G and V. And connectedness of V gives us this module is irreducible if and only if non-trivial definable connected proper G invariant subgroup of V. And here I have some results in small ranks. For example, if rank of V is equal to 2, then we have two distinct non-isomorphic group module of finite Morley rank. Namely, either G is isomorphic to SL2K in its natural action. So G acts on K2 by matrix multiplication. Or G is isomorphic to GL2K in its natural action. In rank 3, we have three different cases. Either G is isomorphic to PSL2K. In here, we have 2 by 2 matrices from K, and action is adjoint action. If we call this H, then this action map G to commutator of them. Or G is isomorphic to SL3K in its natural action by matrix multiplication. Or G is isomorphic to GL3K in natural action too. And thank you for listening.